Good afternoon, everyone. On behalf of Department of Electronics Engineering, RAIT, I welcome you all for today's last session of our ATAL FDP on robotics. There is a wonderful quote by Ruzena Badsky. Many people think of robotics as mechanical things, but robotics is also perception and communication between machines. In recent years, unmanned aerial vehicles (UAVs) have become more popular solution for a variety of civil and military applications, including surveillance, photo and videography, and land surveying. Multi-rotor UAV platforms have gained particular attention due to their simplicity in construction and control. It is my proud pleasure to welcome our esteemed speaker of today's session, Mr. Satyanarayanan Seshasayanan. Satyanarayanan has received his Bachelor of Engineering degree in Electrical Engineering from SSN College of Engineering, Chennai, India in 2017. He is currently pursuing his doctoral studies at the Indian Institute of Technology, Kanpur, India. His research interests include robust linear and nonlinear controllers, flight, vehicle and control. Today's title of his session is Laboratory Demonstration of Multi-Rotor UAVs. Now I request you, Mr. Satyanarayanan, to kindly start your session. Over to you, Mr. Satyanarayanan S. Thank you.
Thank you for this warm welcome. Let me share the screen. I do that. Okay. So, very good evening to everyone. So, today I'm be talking about unmanned aerial vehicle. What are the applications, different types of UAVs, which is existing in current literatures. Then we will see the detailed overview of one such type of vehicle. And if you have any questions, you can stop me anytime you want, or you can post a question in the chat box. Sorry. So UAV has huge variety of application due to its small size and can be installed with a high precision camera, which is useful for monitoring and surveillance purpose. So these are the applications where the UAV has been used, which I have seen it or read it in an article. So first, law enforcement. UAV has been used for crowd monitoring. Recently, during the coronavirus lockdown, drones have been used to warn people who were breaching the restriction area. Second is area photography. For taking aerial image, you might have seen drones used in some film shooting or cinematography, and also in marriage functions. Third is disaster management. Here, drones are used to access the situation remotely during the disaster crisis and can supply food or essential items during such events. So, in agriculture precision, farmers recently starts using drones to monitor the crops and also spray pesticides to enhance the crop yield. And geographic mapping, drones were used to get a precise 3D model of an area or a land. So there exists drone deploy software which actually gives a online 3D modeling of a given area or a land. So in search and rescue, mostly it will be used by a police officer or military, where the people getting lost in forest, or child getting lost in some crowd in congested areas. So in such cases, drones has been used so that it can actually span a very large area within less time. Ship and delivery, Amazon started using drones in UK to deliver their package. So it is currently being used there. And wildlife monitoring, you can see UAV to monitor the monitor the animals in forest or mountain areas. So these are, so let's go into the types of UAVs. So based on uh, the lift force, how the lift force is generated, the UAVs are broadly classified into two types. One is rotary wing and the fixed wing. In rotary wing, the rotor actually rotates to generate the lift force, which is lift force means that you are actually cancelling out the weight. So for that, in rotary wing, the rotor actually rotates. So that's why it's called rotary wing aircraft. And for the fixed wing, it's kind of like an aeroplane where the aileron is used to actually lift the vehicle, and the aileron is attached to the both sides of the fixed wing. And there's some recently there are people who are working on the hybrid of these two, which is hybrid vehicle, and you can see this work in uh, uh, one of our labs, like in aerospace department. Dr. Mangal sir and Abhishek sir are working on this hybrid rotary and fixed wing vehicles. So rotary and fixed wing have their own pros and cons. Like rotary wing can have vertical takeoff and landing, and can also hover at a fixed point. So, but in a fixed wing or airplane, you can't stay at one point, or you can't take off vertically or land vertically. So these such thing is not possible in fixed wing. But one main advantage in fixed wing is that you can travel a very large distance as compared to the rotary wing aircraft. So in rotary wing, it is again classified into two main types. One is multi-rotor, and another one is helicopter or a single rotor. By the name suggests, the multi-rotor means there are more than one rotors to actually help to lift the vehicle. And in helicopter, there's only one rotor which is used. And in multi-rotor, in both of the vehicles have some pros and some cons. For example, multi-rotor can be easily controlled and as compared to helicopter, and helicopter has some kind of vibration while you are operating them. But helicopter can be used for a larger flight time, and also can help to lift uh, heavy loads. So, so in this presentation, I'll be mostly talking about multi-rotors, which is especially quad rotors. And recently, researchers are trying to uh, trying to improve the quad rotors maneuverability and its flight time. So we will look into how those are being improved in recent years. So first, going into a quad rotor, we will just look into the what are the uh, main components which are used in quad rotor. So first, by the name suggests, quad rotor is like four rotors, and here the rotor is powered by a which consists of a motor which is a BLDC motor, which I have it right here. And this why BLDC is used, because it is a small size and it has higher efficient, and as compared to breast DC motor, and longer lifetime also. It has a low weight, but high torque, so the ratio of torque by weight ratio is very high. So this very useful when you are want a very high speed. If you want to have a very high speed something, then you have to use a BLDC motor. And so before going into the hardware, first you will first you will have to see what kind of application you are going to work on it. So based on the applications, like if you want race drones, they are like the frame size are like between 150 mm to 250 mm, but it is very difficult for people who are starting to learn quad rotors. It is not recommended to use a race drone because it's very difficult to actually pilot them. But if you are new to it, then I could recommend to use a 450 mm, 450 or or more than that framework to start working on drones. So based on the application or the size of the frame, the motor specification have been chosen. So the basic thumb rule for selecting the motor is that you should the thrust generated by each rotor should be half of the weight of the core rotor. So the minimum thrust should be that much. Minimum thrust should be that much. So make sure that you once you buy some kind of motor, make sure that you matches that criteria. Second most important thing is that we have this ESCs, which is used to control the speed of the motor. So here we have two supplies to it. One is which is coming from a DC supply, batteries, and other end we will connect to the motor, BLDC motor. BLDC motor is a three-phase motor, and this actually ESC acts as an inverter here, which converts from a DC source to an AC, and the speed is actually controlled by sending a PWM signal, which is done by a flight controller, and the frequency of the PWM determines the speed of the rotor. So changing the frequency of PWM, it changes the speed of the rotor. So it's same as synchronous motor also. So and the basic flight controller that we use are Pixar. It is an open source, and Pixar has a lot of other advantages, like you can model them very easily, and there's a lot of package in it. So we can so let's say if you want to change the controller, or if you want to change the filter, common filter, like for estimation purpose, then it is very useful, very handy to use it, and you can change the code very easily. It is based on C++ code, so it's not very difficult to learn it. And so Pixar is actually consists of ARM Cortex processor, which is having 32-bit, and it consists of various sensors like IMU, like accelerometer for measuring the rates, gyroscope for measuring the orientation, and barometer to measure the height, and magnetometer to see how much is the heading. So such things are already embedded in it. So, and there are a lot of ports inside this, which is useful for external peripheral interfaces. So for the basic ones are like buzzer and the switch. So the switch is used to arm the vehicle and like start the vehicle, and the buzzer is used to indicate whether you have started or not. And the second thing is that GPS one. Since if you are operating in the outdoor, then the GPS model is used to estimate where the position of the quad rotor is. So it has actually two ports in it. One is just to for the position one. Another one is a compass. It has a inbuilt compass in it, so you can use this kind of this for an external compass purpose also to estimate your how much your heading is. And the second most important thing is the transmitter and the receiver, where you have a RF transmitter and the receiver joysticks, so which is used to control your drones. This is connected to the Pixar board, and you will use it with you use this joystick to control it. And there's a lot of switches here to actually change the mode, like if you want to control the position, or if you want to control the attitude or orientation. Based on that, you will change the mode. And one switch is used to lift it, and on left and right you can do the yaw movement, and other switch is used for roll and pitch. So such things are there, and those are important things. And another important is the ground station communication, where this is also a radio transmitter and receiver, and you will use a QGON controller or a software called QGON controller, which uses Maverick communication to communicate with the quad with the ground station. So on the ground, you will just start to log the data, or you want to onlinely see how the quad orientation or how the quad moves. So such things can be seen on your on-screen laptop, and you can also try to control the quad using the on-screen keyboard or on-screen joystick. Well, I could recommend not to, because you don't get that much of feel when you're doing that. And Pixar actually has some SD card in it, where it is used to store some data for you to plot it when you done some task and you want to store some data in it. You can store it. But QGON controller, the ground station also actually stores data. But if you are just having only the joystick, then you can actually store data on the SD card also. And the most one is the popular one. So actually, in quad rotor, there are two types of there are two different rotation. The two rotor rotates in the clockwise direction, and other two rotors rotates in anti-clockwise direction. So the reason behind is that to make it most, if all of them rotate in the same direction, then the system is actually unstable. I will tell you why in a minute. And so based on whether it's a clockwise or anti-clockwise, based on that, it is written here on the propeller, like if it is written R, then it is a clockwise rotation. And if it is written L in the propeller, then it is an anti-clockwise rotation. So for clockwise rotation, so imagine a propeller like this. So for a clockwise rotation, it is like rotating in a clockwise direction. So once it rotates in a clockwise direction, the pitch of the propeller is made such a way that it pushes the air down. So once it starts to push the air down, it actually generates a force which is not actually vertically, but it is used with an angle here. So which is perpendicular to this surface. So based on that, there's a two forces. One is a thrust force, and another one is a drag force. So so once it starts to push the air down, so according to Newton third law, there should be an opposing force, which we call it a thrust and a drag force. Thrust force will be perpendicular to it, and a drag will be coming out of this plane. So uh, so now we will go into why quadrotor is classified as an under actuator system. So, as I've said, that the when the rotor rotates, it generates a thrust force and a drag force also. So the thrust force which will be acting along the z-axis. So all the four will be acting upward, and the drag which is acting on it will make it will create a momentum which is also along the z. So we will call them as a drag momentum and a drag torque. So when the rotor rotates, we generally say that it generates a thrust force and a drag moment. So I'm just opening this. So what does it do is like so you have x and y. So here, let's say this is x-axis and this is y-axis, and if you want to move along the y-axis with this orientation, you can't able to move it. So so in order to generate a force along y-axis, you have to either roll I should have said what is roll is. So the roll is nothing but rotation about x-axis. So if you are fixed your x-axis like this, then the rotation of that is called a roll. And if you have fixed the y-axis like this, then the rotation about that arm is called yaw, pitch, and for the z-axis we call it yaw. So for x it's roll, y is pitch, and for z is yaw. So for in order to move the quad from a point A to point B, then what it has to do is first it's to generate a force along that direction. In order to generate the force along that direction, the quadrotor has to change its orientation. So, for example, if you want to move only on y-axis, so the quadrotor first rolls. So once it rolls, it can't roll like this because you have to maintain the height also. So it rolls some angle. So in order to generate some force along x-axis. So and also tries to maintain the weight force which is acting downwards. So once it rolls, it starts to accelerate, it starts to move, and the velocity starts to increase. Once you reach the suitable velocity, you roll back to zero. Then you move at that velocity constantly. And if you want to stop at a particular point B, then you have to generate a reverse thrust. So in order to generate a reverse thrust, you have to roll it in opposite direction. So you start to decrease. So the acceleration is negative. So the velocity starts to decrease. And once you reach that point, you roll back to zero. So such things. This makes the quadrotor and actuator system because you can't decouple the position and as well as the orientation. So even even though the quadrotor has only 4 inputs and there are 6 degrees of freedoms, that is the position like x, y, z, and the roll about the axis, that roll, pitch, yaw, and so there are 6 degrees of freedom. So but it has only 4 inputs, as I said, like 4 speed, that's 4 speed of the motor. But even in the hexacopter, like it has 6 rotors. Even though it has 6 rotors, it is actually considered to be a under actuator system because of this, where you can't generate a force along x or y axis without either rolling or pitching. So the position is actually coupled with the orientation. So uh, generally, the quad rotor, the conventional quad rotor, are classified as an under-actuated system. So we will go into this control mapping. So I've said that when the rotor speed increase, the thrust actually increases, and based on the blade theory, the each thrust generated by each thrust generated. So let's say F1, F2, F3. This is F3, this is F2, and F4. So each and each F1 is directly proportional to the rotor speed square. So and it is always acting along the z-axis. So that's why you will just add all the terms of the rotor speed, like F1 plus F2 plus F3 plus F4. And for the roll, I have said that roll is nothing but rotating about x-axis. You keep your thumb like this, pointing along the x-axis, then you curl it. So wherever it curves, that is the roll, the positive roll. So for the positive roll, this two thrust, like this one and this one, should be high, and this two should be low. So in order to give a positive thrust, so positive roll. So for positive roll, the F3 and F2 should be positive, and F1 and F4 should be negative. So that's what is written here. And for the pitch is just along y-axis, you have to curl a finger. So if you curl, it is like this. So F1 and F3 should be positive, and F2, the back two, should be negative. So in order to give a positive pitch, so that's why you have a mapping like this. And for the yaw, so let me keep it down. Yaw is due to that drag force only. So when the rotor is rotating, it is rotating in a anti-clock. One is rotating in anti-clockwise direction. So the thrust FD will be generated along this direction, and for one, and for the two, it will be the it is rotating like this, so it will be like this. And for 3 and 4, similarly, FD3 and FD4. So, and what you do is, like, you know that if you have a vector R and the force F, then the torque is nothing but R cross F. So what you do is you just do the same thing, and you will notice that the one which is pointing down are considered like I have taken the down to be a positive z-axis. So the if you do R cross F, then you will see that for the first rotor, the moment will be downwards, and for the second one is also downward. So let's say down, I put it point, and for this two will be coming out, I put it cross. So that's why you will have plus sign here. So this is the main reason why we have two to be rotating in a clockwise direction, other two to be anti-clockwise direction. If all the four were being rotating in the clockwise direction, then you will start to yaw continuously, which is actually unstable. So that's the main reason why we have two to be clockwise and other two to be anti-clockwise. So before that, I will just say how you will, so given U1, U2, U3, and U4. So U2 is called roll torque, U3 is called pitch torque, and U4 is called yaw torque. So given U1, U2, U3, U4, how do you find uh, the map? There's a map A and your omega 1, omega 2 square. So you can write this U1, U2, U3, U4 in this format, and I hope you can see it. So, and based on that, omega 1 square, omega 2 square, omega 3 square, omega 4 square is nothing but your A inverse U1, U2, U3, U4. So given U1, U2, U3, U4, uh, the map for finding the required speed of the rotor is calculated by this one. You may wonder whether this map that on the right hand side will it always generate a positive value, because on left hand side it is always positive, but on the right hand side will it always generate a positive value or not? So what Pixar does is that you actually, once you calculate this, you will normalize the values. So normalize the value between -1 to +1. So so once you normalize the value to -1 to +1, so the omega for -1 it is mapped to 1000, some scale 1000, and for positive one it is mapped to 2000, and for in between 1500 it is used to hour it. So that is used just to hold the cord. So just to be that in just to hold the cord, or just to hover the point, you will have 1500 as a RPM. It's just a the needed RPM to just to hover it. And for -1 you will go to 1000, and for the +1 you will go to 2000. You start to increase the speed. So based on that, Pixar uses it, and most of the controller, whatever the controller you're designing, you will just map it to this. You first normalize them between -1 to +1 by taking the magnitude, and you normalize them. And the -1 will be mapped to 1000 speed, and +1 will be mapped to 2000 speed. 2000 is the maximum speed of the rotor, and in between, like 1500 is the point where you will just hover the vehicle, like it is just hovering. And so now we will go into the controller architecture. So as I said, from the position control, you can use any PID control or any nonlinear control you want. So which from the error dynamics, error of the position, that is x minus xd, y minus yd, and z minus zd. You will use some kind of a controller, either PID controller or any sliding mode controller or any nonlinear control you use. You generate the required force along x, y, z. So these are all in with respect to your initial frame, that is your non-moving frame. So, but the body actually is changing its orientation, and so in order to visualize in the body frame, so let's say this is initial frame, and you have some body frame. This is body Z, body X, and body Y. So in order to, if you have a vector in the body frame, to convert to initial frame, you have some kind of rotation matrix, which will convert body frame to initial frame. So let's say this is F. So you have some kind of R into F to which will convert a vector of this frame to this frame. And let's say this is to be F dash. So, and the R here depends on your roll angle, your pitch angle, and your yaw angle. So based on that, So f dash, you know that this is your desired f dash, and f is nothing but in on the body frame for the quad rotor. So let's say x, this is the one which is pointing towards you, is x and y, and z is upward. When the body rotates, the x and y also changes. So, but the thrust generated by the rotor is always along the z body z axis. So the f here is nothing but r into 0 u1. So along x and y axis, the thrust is always 0 with respect to the body. So you will have r 0 0 1. So uh, so what does this do is, like, you have a position, and you have found out your desired force or desired thrust, and you have a converter which will convert your which will try to find out what should be your desired phi d, desired theta d, an external input, like how much heading you want, like how much angle of heading you want, that you will give it as an external input here. So based on that, you will try to find what is u1, phi d, and theta d based on these three equations. So you just equate them, and you will find out those coefficients. Once you find out this phi d, theta d, and psi d, you will use a attitude controller, which is then is same as you can use same PID controller or any nonlinear controller, which will try to find out what is your U2, U3, and U4, and the converter to which I have discussed earlier, which is nothing but that A inverse something. So U1, U2, U3, A inverse will just give you your desired rotor speed, which is given to the plan, the quad rotor model. So, and the feedback, as I said, the Pixar actually has sensors which will give your desired rates, and what are the rates and the position of the quad rotor is. So based on that, you will actually you use that. Actually, they will use a Kalman extended Kalman filter to estimate those variables like the position and the orientation. And once you have the desired and the estimate, you just find out your error dynamics, and from there you will just use any PID or a nonlinear controller to control them. So next we will go into this variable pitch quad rotor. So in general, quad rotor has one main disadvantage is that you can't have a very high flight, very long flight time. Like it is being limited to 10 to 15 minutes, depending upon what kind of if you are using full thrust, like if you are operating with a very high speed, then the maximum time is limited to 10 minutes at max. So in recent 2015, Marka and Cutler actually developed a hybrid of an helicopter and a quad rotor, which is actually known as a variable pitch quad rotor. Let me take it out. It is actually a little bit bigger. So sorry for that. So variable pitch quad rotor, actually what does it do is it has one rotor in it. So it is being powered by only one rotor. So same as a helicopter, helicopter is also being powered by only one rotor. And when the rotor rotates, all the four propellers rotates in the same in the same speed. So, but as I said before, the diagonally opposite will rotate in clockwise, and other two diagonally opposite will rotate in same direction, and other two will rotate in opposite direction. So and how does the differential thrust has been generated by the each rotor is by changing this pitch angle. So if I change, let's say if it is rotating in a clockwise direction, then you can see that this part is flat here. So when the air attacks, it pushes the air down. Thereby, you are able to generate a thrust upward. So instead of changing the speed of the rotor, you change the pitch of the rotor. And so the another main advantage is that in the conventional quad rotor, you can't generate a reverse thrust, but in variable pitch, you can actually generate a reverse thrust by pitching in opposite direction. So I was in pitch like this. Now I've changed the pitch angle in opposite direction. So if it is rotating, then it pushes the air upward. So thereby you will generate a thrust actually down. So which is so thereby the control bandwidth of this variable pitch is high as compared to conventional quad rotor. And another main advantage is that it has only one motor, or you can use one rotor only. So you can use a engine type to actually such types of vehicle. So I will quickly say what are the main advantage of this. So as I said that it is all the four are rotating with the same speed. It is being powered by a single power plant called fuel. You can use a fuel engine. So if you are using fuel engine, then you can actually have higher flight time as compared to a battery. So and scalability and size and weight can also be increased, because if you are using gasoline or something like that, then it can generate high amount of torque or high amount of thrust to in order to increase overcome the weight force. And generation of reverse thrust. So as I said, the variable pitch actually changes pitches in both directions. So you can generate thrust in upward as well as downward also. So it is very useful when you are doing that 180-degree flip. So such 180-degree flip is not possible in conventional quad rotor, but in variable pitch quad rotor you can use it. So thereby the maneuverability of variable pitch has been increased as compared to the conventional quad rotor. And finally, the control bandwidth. It has been done by one of this article, same as the article author is same as Martha and Cutler, where he has explored the control bandwidth. That is, if you are giving the rate of change of thrust for the variable pitch is very high as compared to the conventional quad rotor, and the reason behind is because of its rotor inertia. Here you are using just a servo to change the pitch angle, but there you have to just you have to use the rotor to actually to change the thrust generated by the rotor. Rotor speed to change the thrust generated by the rotor. So if you see their paper, they have done it experimentally and validated that if you are changing the thrust, let's say if you want to move from 2 Newton to 5 Newton, the time taken for variable pitch is very high as compared to the conventional quad rotor. So, and let's go into the control mapping. You can see that it is almost same as the conventional one. So the thrust generated by each rotor is directly proportional to that pitch angle. So, and we will have some kind of a thrust coefficient Ct. So each rotor has a thrust coefficient Ct, and the relation between the pitch angle and the thrust coefficient is given by that theta naught, and the control allocation almost the same as the previous, like thrust U1, roll torque, pitch torque, and yaw torque are almost same. But if you say the yaw torque, it is actually a non-linear term having like 3 by 2, and for but in our case it was just a rotor speech pair. Uh, Here it is actually a non-linear, but people will approximate them as CT1 itself, because because CT1 is actually very small, and there are other algorithms where you don't have to approximate them. What they have done is that they have taken the linear model of this, like approximate to using Taylor series, and from there they have estimated the trust coefficient, and so the map is almost same, and and we use this once the trust coefficient is done, then we will use this formula to actually determine uh, what should be the pitch angle. The gamma, C, alpha are all constants, and it does not vary with the vehicle. It's just a constant with respect to the propeller that you have chosen. You can look into the paper for what kind of values that they have. They have plotted the values and they have shown these are the values for it. You can look into it. So but if you see this variable pitch core rotor is also an under-actuated system. Even though you can generate a thrust in a reverse direction only, you can't generate a thrust along x or y axis without rolling and pitching. So such a disadvantage makes it to be an under-actuated system, but it has a wide variety of other applications, like it can fly, the flight time has been increased, and the control bandwidth also can also increase, and it can carry heavy loads. So people are started using or trying to find a best controller for such vehicles. And as I've said, I have only recently people are started using some kind of optimized technique to actually vary the speed of the variable pitch also. So here the speed is remaining constant. I have assumed the speed is remaining constant, and I try to find out what should be the pitch rate. But since some recent works where there people are started to find optimal control allocation map, where you actually change the speed of the motor also, and and the pitch angle, and you try to find out so like let's say you want to minimize the energy, or if you want to minimize uh, the time taken to reach a particular point. So those are considered in the optimization function, and they try to find out the best optimal solution for control inputs for the variable pitch core rotor with varying speed. Uh, Finally, what we have been working on is the new one, which is called the stilt quad rotor, and it is a fully actuated quad rotor. What I mean by that is that you can actually decouple the position as well as the orientation. So uh, uh, this actually recently got published in 2019, and people started there are something like tilt hexacopter also, and they are started working on that because it has you large angle. We can go to very large angle, whereas tilt hexacopter has been limited to like how the quad rotor has been limited. The maximum roll and pitch angle has been limited, even though it's a fully actuated. The maximum roll and pitch angle has been limited because you have to maintain the weight. But if you are going with hexacopter, there is no that amount of limitation. Like you can have it like a 90-degree pitch also in hexacopter, tilt hexacopter, and they recently researchers are started working, and in India, we are only we are the, as of I know, we are the only people who are working on tilt augmented quad rotor, and there are a lot of open problems in it. Uh, to how do we actually design desired path, or how do we actually avoid obstacles, or how do we come up with a better control allocation for such vehicles. So let me actually show you what we have it in our lab. Oh, sorry. So this is a tilt exocopter. As I said, what is tilt quad rotor? What I said was that it is same as a conventional quad rotor, but it has a ability to each rotor has the ability to tilt. So so without so if I able to tilt them, you can actually generate a force along x or y axis without rolling or pitching. So thus you can actually decouple the position as well as the orientation. So so let's say this is the one which is pointing towards you is x-axis, and this is y. And if you want to generate a force along y, you just have to tilt them, uh, tilt the two rotors along the same direction. So you will generate a force along y axis, and you can't tilt like 90 degrees or more than something, because you have to overcome the weight also. So so that makes it a little disadvantage as compared to if you are going with a tilt hexacopter. But this tilt quad rotor is a fully actuated, which means that I can decouple the position as well as orientation, and we will I will so show you some. Uh, I will show. So this is the basic control block diagram which has been done, and I'm not going to discuss what control allocation that we have used for developing, because it's still in the process of our paper is still in the process of accepting it. So but you can also think of how do we actually have a control allocation, because this acts it has 8 inputs. As I said, it has 4 rotor speed, and 4 each rotor has one particular tilt angle. So it has 8 inputs, and 6 and has 6 degree of freedom. So the number of so since it is over actuated system, you can think of some kind of optimization technique to come up with a control allocation, which can be minimizing the energy, or minimizing the time taken, or if you or part planning. If you want to move from one point to another with the optimal trajectory or something, you can come up with a control allocation scheme based on that also. So yeah, so since I've said that you can decouple the position and orientation, there are 2 different blocks now: position control and attitude control. Attitude control is nothing but orientation control, and from there you will generate what should be your desired force along XYZ, and desired momentum along roll, that is roll, pitch, and yaw. And there's some control allocation which maps from this desired values to your rotor speed and tilt angles. I thought I will show some videos before I Uh, so this is one of our not one of our this is from Mangal sir's lab. They have done a variable pitch quadrotor with an engine. So what we have in our lab is a motor type, and for engine also they have done it, and it is they are controlling using joystick as of now, and it is just move. It is able to control them, and one person is actually controlling using joystick. It's a very long video. Close it. And one of my previous PhD senior actually done the tilt rotor, and you can see the tilt mechanism. And so he has tested for yeah, for waypoint navigation with zero orientation. So that is you are just maintaining zero orientation and you are able to move it. This is very helpful while you are doing some kind of you want to land on a high speed vehicles, or then you have to maintain the zero orientation. So in order to land it vertically down, when the vehicle is moving very high speed, then you have to land it on a vertically down. Then it is very useful. And this experiment that landing on a high speed vehicle has been done by the same PhD guy. You can refer his paper also. But his control allocation does not actually minimizes anything, but it's actually useful when you are just doing zero orientation and able to track desired path. Yeah, yes, trying to move the tilt quadrotor in 4 points on a on a square. So uh, it was able to do it. He actually going behind because if something happens, then he has to control them. Otherwise, is no need of if it is controlling perfectly, then it's no need. It's just for safety purposes. Is actually doing it, but if you can see it comes back to the same point where he has started and it lands. So and so finally I will show yeah, so I will tell a software where you if you want to develop yeah, if you want to develop an algorithm that you want to check whether it is working or not, or so for that we have something called as Gazebo. It's a ROS, it's a robot operating system, and Gazebo actually has can model any 3D robotic system, and with any complex environment, indoor as well as outdoor. And it is very easy for people to start with because it is just adding components wherever you want to, and they are inbuilt environment inbuilt vehicles also like quad rotor or robotic arm. Some of them are already in there, and if you want to design your new vehicle, then I recommend to you to use a gazebo. And actually Pixar actually supports a gazebo to communicate. So what Pixar does it communicate with the gazebo using a serial USB cable, and the gazebo is run on the laptop. So Pixar sends the actuator input, whereas the gazebo sends the sensor inputs like position or the orientation. That sensor inputs, even the GPS inputs, and also gyroscope, accelerometers, sensor, and Pixar actually estimates the position and the orientation, and tries to find out the control inputs for your vehicle. and it is communicated to gazebo. And there's a ground control, Q ground control, where just for ground for just for ground control. Like if you want to change the mode or if you want to save the data, then you have to use a Q ground controller, and they are controlled. They are communicated using a Mavlink interface. It's a micro air vehicle communication something, and it is as of I know, it is communicated using a radio frequency only. So, so what I have done for my for which I'm going to show is organ the loop with desired trajectories which I have defined here. So when the height is less than 2 meters that you are just going to hover it, your phi and theta t are set to be 0. And once you went to 2 meters, then you start to do the sinusoidally varying phi roll and pitch angles. And so for the position, this is for attitude, that is orientation. And for the position, we have decided the xd to be 0 and yd to be at a linear function, linear time varying function. And once it reaches the, let me draw what happens here. So what does it do is, like, you are starting from this point and you go to 2 meter in height, then you start to move. Actually, we're not actually going to 2 meter. You start to move in both x and y direction. So in z direction, you move till till 5 meters, and because it is maximum is 5. And in y, you are just moving till 10-meter radius. Once you reach the 10-meter radius, you start to circle with a sinusoidal varying phi d and theta d. So this trajectory has been tested on hardware in a loop simulator, which I'm going to show now. So on the left hand side, you can see here a green color arrow mark, which is actually a Q ground controller. On the right hand side, you will see a gazebo one. So if you see that it actually goes, it is not exactly the straight line. There's a bump in the curve because the attitude at that point is actually changing to that sinusoidal varying. Before that, it was just zero orientation. Once it goes till that 2-meter height, it starts to roll and pitch sinusoidally, and is still trying to track the circle. And you can see the roll angle and the pitch angle changing varying sinusoidally. One is sine and cos, so there will be a phase difference of 90 degrees. So one's at 0, then the other will be at 50 and something like that. So that's all I have today. Thank you. If you have any questions, you can ask me. I still have 15 minutes to go.
Are there any questions from the participants? Sir, what are possible applications of AI in this UAV?
So as of now, you can use AI to actually have the control allocation here. People have not yet explored such things because like you need a map from FD and MD, like force, the desired force to your desired roll angle, tilt angle, and your rotor speed. So for that, you can use some kind of a neural network or any AI kind of thing to train them to find a map which actually maps from this to that, and you can use that map for actually to control or to find a control allocation which is useful to for certain applications. So for that you just start with a MATLAB simulator that okay, I want to go this to that point with less time or something like that. And once you reach the desired points, you collect those points. Then you will find a control allocation which where the neural networks or any AI trains them to calculate the control allocation map from this to that. So those are not yet been explored. You can think of them, and for any quad rotor also, because those constants in the quad rotor or in a variable which are not like pre-known or before. People assume that this is the constant, but you can actually train them, and and you can find those constant like using AI. I think that's the one way of going into it. And also for trajectory tracking, trajectory generator also you can use AI to for avoiding obstacles with a limitation of pitch angle and roll angle. You can see that in my simulation I have limited my pitch and roll to be 50 degrees. So that is the maximum pitch and roll that a tilt rotor can take, which I have done. But if we want so if you are designing a trajectory such a way that it should avoid obstacles, and also within that range of pitch and roll angle, then it is very interesting to use AI in that also. So there's a lot of scopes on them.
Okay, thank you, sir. One more question from our participant, Rohit Kalyani. Is it possible to implement auto-tuning of PID on the fly? Can you suggest any methodologies for the auto-tuning?
There's adaptive control existing in literature for uh, tuning or if you are using for adaptive control, it is like it is guaranteed that you will have the desired control or desired you will track the desired path. But for tuning purpose, like if you are trying to tune them, then it is very difficult to tune them, because as of now the one tune that always works is that the default tune only. I have tried it many times, so I don't know why any other them will not work, and some of them becomes unstable after some point of time. So I think you can use adaptive control as my suggestion will be on that, and some you can refer to some adaptive control on quad rotors. There are a lot of literatures that have been done where they're tuning. They have used some kind of gain scheduling some techniques to estimate the gain for PID. So you can use them also. But as of I know, I don't know how online you can change the KP, KD, values. It's very difficult for me also. I've not yet been exploring that. So yes.
Okay, thank you, sir. Our question is there. Are there any models for UAVs specially designed or any modified for rescue and firefighting activities?
Uh, uh, for firefighting, in in industry, people are still using drones because of their small size only, and it can move at a very high speed also. So for if you want to design your own quad rotor or your own aerial vehicle, then the main thing is to be that it should be much more advantage than the existing ones. So this tilt core rotor has some advantage, but still it has some disadvantage. Like you can't have larger flight time or something like that. So for firefighters, you should have some kind of material to resist some fires or something like that. So such material can be used to used as a frame for designing the core, and you can use them also. I don't think there's a restriction for it.
Okay, thank you, sir. Any other questions from the participant? Then we can move ahead for vote of thanks. So, on behalf of Department of Electronics Engineering RIT, I would like to sincerely thank Mr. Satyanarayanan S for this
Yes.
excellent demonstration. So, as we know, truly our UAVs have played a very important role in many places in this COVID times. So,
Yeah,
it
yeah.
was highlighting all these features and demonstration. So, indeed, it was a very informative session, and I'm sure everyone have benefited from this talk. So, with this positive note, I would like to conclude this session. Thank you, Mr. Satyanarayanan S.
Yeah.
and
Thank
participants.